6 presentations, 5 online and 1 in presence. And I can see the people connected, and I say hello to all the people that are ready to deliver their presentations online from Zoom. And also, I apologize for the 20 minutes delay or so, because we had the NSF consortium over the lunch break. As you know, like 10 students from US universities have been supported to attend this meeting with a waiver for the registration fee by NSF. So we had this event, which was sponsored by NSF and is gratefully acknowledged from the ISER community. Okay, so the first paper is titled CMP-CC is Corridor-Based Model Predictive Contouring Control for Aggressive Drone Flight, and the presenter is Jailin Ji, who is connected. So if you can just put Jailin Ji up on stage. Can you hear us? Can you talk, Jailin?
Could you hear me, Professor?
Yes, perfectly.
I could hear you. Oh, okay.
So you can start sharing your presentations.
Okay. Just wait a minute. Could you see the PowerPoint?
Perfectly. We can see it. Yeah, sure.
Okay.
You may hide the comments maybe, or just the next slide. If you can make just the main slide big, because we can see your slide and the next one. So I don't know if you have a way to avoid the.
You mean you could see the comments? Right?
No. If you can avoid the preview of the next slide, so that your slide is bigger on our screen.
Let me see.
I'm told you should share the PowerPoint before starting, before projection. Just open your PowerPoint and share. Yeah, now share.
Now
project. Yes, perfect.
It is fine. Okay.
Yeah, go ahead, please, go ahead.
Okay. Thank you.
Go.
Oh, hello everyone. Now let's start. I'm honored to have the opportunity to speak at this conference. And today I would like to present my paper, CMP-CC, Corridor-Based Model Predictive Controlling Control for Aggressive Drone Flight. In recent years, the autonomous navigation of quadrilaters develops rapidly as it plays an important role in real-world applications. Among the criteria of designing autonomous quadrilaters, generating optimized trajectories and tracking the flight path precisely are 2 critical components in the action aspect. Here's our previous work, T-tree plan, a cascaded planning framework with global trajectory generation and local collision avoidance. The system can offer agile flights under the user's preferable routines. And however, the planner and controller of a quadrilateral are mostly independently designed, making it hard to tune the joint performance under the disturbance of the environment, such as the wind. So there's a gap between the planner and the controller. To bridge this gap, we propose an efficient receding horizon, a local adaptive low-level planner as the middle layer between our original planner and controller. There are 3 main features of our method. Firstly, our method balances tracking accuracy and traveling progress naturally with these disturbances. And secondly, corridor and terminal speed constraints guarantee safety and feasibility. And the third feature is the quadratic programming formulation with less than 5 milliseconds onboard solving time. This makes it can run real time on board. Our method is inspired by this work, an application of MPCC as the planner for miniature car racing. The safety constraints are established by modeling linear functions from the boundary of the racing track. Just like this. However, such constraints are not directly available for quadrature in unstructured environments. Now let's see our problem formulation. Given a global reference trajectory, here PT, we design a retiming function T tau here to map the original time to the new time of variable tau. Then the derivative of T indicates the traveling progress. And that is to say, when it's greater than 1, the drone travels faster than the reference trajectory. When it's less than 1, it means the opposing situation. We also designed the adjusted local trajectory as tau. Then the tracking error is defined as the distance between P and S. The objective is to trade off the tracking error and the traveling progress. Under the safety constraints, this will be introduced later. After the discretization and linearization, we formulate the problem as follows. A typical path following MPC with a retiming variable theta. We model the system as a third-order integral model. The states are given by x, y, z, theta, and the first and the second-order derivative of them, v and a. And the input is given by jerk, the third-order derivatives of x, y, z, theta. They are discretized by delta t with the length of predictive horizon n. Thus, the optimization problems turns into receding horizon MPC with linear state transfer equation here. And we can say the objective is nonlinear because of the term p theta. Thanks to the framework of receding horizon, we linearize this term around the optimized result in the last horizon. Thus, the object function can be represented as quadratic. And now let's see the safety constraints. A safe flat corridor is a series of connected polyhedrons representing safe area around obstacles, which is generated while global planning. Leveraging the safe flat corridor, we generate a polygon tube for each state during optimization. The polygon tube is generated as the intersection between the corridor and the normal plane of each state of the global trajectory. And each state at an optimizing time step corresponds to a single polygon tube. Yeah, this is our safety constraints. Besides, considering the short side of the limited horizon, we set a terminal speed constraint. Restricting the terminal speed ensures feasibility while significantly shortens the planning horizon. Here is the hardware and the software architecture configuration of our experiment. We use a self-developed quadrator with an Intel RealSense camera, D435 stereo camera, and a DJI N3 flight controller for state estimation. All modules run solely on a DJI Manifold 2C onboard computer, and our system inherits the localization, mapping, and the global planning from the T3P3 plan system. And here is a comparison between CMPCC planner and the ordinary planner under the wind disturbance. We can see without the proposed CMPCC quadrator tracks the global trajectory generated by T3P3 plan with only a feedback controller and collides with the nearby obstacle soon. However, thanks to the safety guarantee, the proposed CMPCC replans a safe trajectory and rejoins the global reference trajectory quickly under the wind disturbance. And we also apply challenging force disturbance to the drone to test the performance of the proposed CMPCC planner. And here is the top-down view of the experiment. We can see the performance of our planner. Okay, now let's see the spatial and the time profile of the circumstance under contact disturbance. The red line denotes the trajectory of CMPCC. The blue one denotes the global reference trajectory, and the magenta one denotes the trajectory without a disturbance. From the left, we can see the isolation occurs near the hit position, but the CMPCC planner soon converges to the global one. From the time profile, we can see that the instant force disturbance changes the temporal distribution of the optimal trajectory, resulting in the delaying of the trajectory of CMPCC relative to which without the disturbance and the global trajectory. And here are some more tests. This test shows the robustness of our system. Okay, thanks for listening. Any questions?
Thank you very much. The paper is now open for discussion. Questions?
Oh, yeah? Yes.
May we have a mic for...
Thank you for this very interesting presentation. My question is, what is the advantage of this middle level contour MPC than the letting MPC generate its own trajectory by giving all the constraints? I mean, one MPC that actually works as a controller, also as a planner, and giving all the constraints. Is there a apparent advantage?
I think your question is the corridor constraints. Is there any advantage of the corridor constraints? Is that right? Your question?
My question is there any advantage of this architecture? I think you have like a global trajectory, then you have this contour controller, then you have like low-level controller. Instead of this, we can have also MPC controller that can directly generate its own trajectory. So what is the advantage of your architecture over this?
I think the largest advantage of this architect is the retiming term. I mean this one. The traditional MPC formulation could make the drone tracks the global trajectory precisely, but our architect could we can assume there is a ball running on the global trajectory, and the drone just trace the ball. If the ball the ball's speed, the speed of the ball is also can be optimized. Just like when the disturbances occur, the temporal distribution could be adjusted, just like here.
Usama?
Yes, Well, thank you for your presentation, and I just wanted to make clear in relation to the previous questions. There is actually a methodology, well-known methodology called elastic planning that involves essentially starting with a plan and then trying to modify the plan in real time using an elastic bubble band, or for more complicated systems that involve more degrees of freedom, we use elastic structure that brings guarantee so the robot that can move from one part of the space to another part of the space. So this is very similar to your approach, and I think the idea is very interesting because now you can modify the plan in real time as you discover your environment. So is that what you're doing here?
I think you mean is similar to elastic planning.
Yes.
And I think I'm not quite familiar with the elastic planning, and I think my proposed method could just like here, I can balance this tracking accuracy and the children progress, and the children progress is just also be optimized jointly. I think perhaps it's similar to the elastic planning.
Yeah, I mean, you have polyhedral connections, and you have to guarantee that you have a passage between them, and you have a lot of similarities. And I think this could be clarified in the, I mean, from the beginning, so it will be more intuitive to capture it. I think you have it in slide 3 or 4 or 5 when you are describing the connections. In any case, I don't want to take all the time for this.
So slide 6, I guess.
6, yeah.
You mean this slide, right?
Yeah, it's sort of similar to the bubbles. So.
Could you say my slides?
Yeah. This is the slides. Very good. Thank you very much. Thank you.
Okay.
Oh, okay.
Andrew, why don't you set up in the meantime?
I beg your pardon?
No. I'm telling the next speaker here in presence to set up the computer.
Okay.
So we'd like to thank you again, Jalene, for the excellent presentation. And please stay connected because we will wrap up the session with the discussion in about 1 hour from now, okay?
Okay.
Thanks again.
Thank you.
Okay, bye-bye for now.
Thank you.
Okay, the next paper is titled Radar Inertial State Estimation and Obstacle Avoidance for Microaerial Vehicles in Dense Fog. Andrew Kramer, please.
For that. Okay, we've got that sorted out. As Bruno said, I'm Andrew Kramer. I'm presenting my work on radar inertial state estimation and obstacle detection for microaerial vehicles in dense fog. Now, the overarching problem that I'm dealing with here is that an autonomous flying robot must be able to build a model of its environment and localize itself within that model. As an example, in this video, we can see a robot building a model of its environment using an occupancy grid with LiDAR and localizing itself using visual inertial odometry. LiDAR and vision are commonly employed in achieving localization, mapping, and higher level perception problems. Depth cameras, GPS, and inertial measurement units are quite popular as well, and these work fantastically when conditions are favorable for them, i.e. when the air is clear, when ambient light is plentiful, and in the case of GPS, when there is an unobstructed view of the sky. But when conditions aren't favorable, methods based on these sensors tend to degrade pretty quickly. For example, this video shows the same space we saw earlier with a robot using the same sensors and algorithms we saw in the first video, but now the space is filled with dense fog. We can see the VIO estimate jumps around a lot. It's not quite sure where it is. And the occupancy map is filled with erroneously occupied cells. And these challenges aren't just found in lab spaces with fog machines either. For instance, robots in search and rescue missions in built and natural environments often face challenges from these so-called visual degradations. So this presentation is going to be organized as follows. We've already gotten past the introduction, but next up I'll go over a few bits of related work, and then I'll discuss my methods for radar-based state estimation and then radar-based obstacle detection. And I'll lastly demonstrate the two systems working together and present a couple of conclusions and directions I think would be useful for future work. So, several methods for state estimation in foggy environments have already been presented. Thermal imaging in particular has been shown to work fairly well, but there is another sensor type that I feel hasn't been adequately investigated, and that's millimeter wave radar. Very few methods have been presented using radar, and although many of these methods have shown very impressive results, including quite a few now from Paul Newman and Ingmar Posner's groups at Oxford, these have generally been limited to a 2D environment. And further, they mostly rely on very heavy and power-hungry radar sensors that while they're easily carried by a car, as you can see here, would not be appropriate for a small and agile robot like a microaerial vehicle. The work I'm presenting is designed for a three-dimensional environment, and it uses lightweight and low-power radar on a chip paired with a MEMS IMU. In this image, we can see our sensor rig mounted on a small quadrotor drone, along with an Intel NUC computer for onboard compute. As I mentioned earlier, this project has two components, state estimation and obstacle detection. I'm going to discuss the radar inertial state estimation method first, and then proceed to obstacle detection a bit later. I used a Texas Instruments AWR radar sensor, which is pictured here. It returns targets parameterized by their range, Doppler velocity, and azimuth and elevation angles. Now, if I assume that the sensor platform is moving and all of the objects in the scene are stationary, then the velocity of objects in the scene relative to the sensor has the same magnitude but opposite direction as the sensor's velocity. An object's Doppler measurement is the projection of that relative velocity vector onto the ray between the sensor and the target. So if we have Doppler measurements of many targets distributed throughout the scene, we should be able to regress the local frame velocity of the sensor platform. That's reflected in the Doppler sensor model that I'm using, where the true radial velocity of a target is the dot product of the local frame velocity of the sensor and the unit ray between the sensor and target. Now, it would be possible to use this model alone to estimate the sensor platform's local frame velocity at a single time step, but radar sensors, especially the lightweight automotive type ones that I'm using, tend to be quite noisy, so single time step velocity estimates from radar alone tend to be fairly noisy as well. That's why I actually jointly estimate the system state at several time steps using IMU measurements to constrain the change between adjacent states, as we can see in this factor graph representation of my system. I estimate this state vector, which includes the robot's global frame velocity, its orientation, and also the gyroscope and accelerometer biases. I estimate that by optimizing the cost function shown here, which includes a Doppler factor and an inertial factor over a sliding window of k successive Doppler measurements. I compared the velocity estimates that I get from this system to those from a visual inertial odometry method, specifically the one that's implemented on board the Intel RealSense T265, and a LiDAR method using motion capture for ground truth. This plots the errors over time for each method for a typical run, with, I should mention for these runs, sensing conditions were as close to optimal as we could make them for all of the sensors, so no fog, plenty of ambient light. And I would say these plots show that the radar inertial system's velocity estimates are certainly on par with the other state-of-the-art methods when all of the methods are performing their best. Now, the system actually produces velocity estimates that, are sufficiently stable and accurate to be used in closed-loop control of an MAV, as we demonstrate in this video, as soon as it loads. Oh dear. Okay, seems to be going now. Clearly the state estimates the MAV is getting aren't perfect, but they are accurate enough that the MAV is able to take off and hover in place for at least a short time with minimal drift using only the radar inertial velocity estimates as feedback. Now, the second component of this project is the usage of radar for obstacle detection. Occupancy mapping is commonly used for obstacle detection tasks, but using radar for occupancy mapping can come with some significant challenges. Firstly, commonly available occupancy mapping packages, such as the one provided with ROS, assume a beam sensor model where rays are cast from the sensor to each point in a scan, and the occupancy probability for a cell in the map is increased if the cell contains a ray endpoint and decreased if it's traversed by a ray. But this is a problem for radar because radar doesn't cast a discrete set of rays. And it also might have detections at multiple points along the same ray. So to address this, I modified the ROS Octomap package with a volumetric sensor model in which the occupancy probability for a cell is simply increased if it contains a radar return and decreased if it doesn't contain a radar return but is still within the sensor's field of view. Even with this modification, though, we run into a fairly large challenge with radar-based occupancy mapping as demonstrated in this video. The problem is that radar scans just contain a high number of spurious returns that represent noise and not any real feature of the environment. So we can't be terribly confident that any individual radar return represents occupied space. This results in a very sparse map that sometimes captures salient objects like the car that we can see on the left side in the LiDAR point cloud, but sometimes objects are just missed, like this pillar coming in from the right. So what we really need here is a way to discriminate between true returns and noise in a radar point cloud. I do this using a learned noise filter that I implemented using the PointNet segmentation network. It attempts to identify which points in a radar scan correspond to noise and which are true returns. This video should quickly demonstrate the weekly supervised training procedure that I used. Basically, I have spatially aligned LiDAR and radar point clouds. The radar point clouds are in red and the LiDAR are in green. And if a radar point occurs within a threshold distance of the nearest LiDAR point, it is labeled as keep, and all of the others are labeled as discard. Those labeled point clouds are what I actually use to train the point net segmentation network. Now this video shows my modified Octomap running on the same data we saw previously, but with the addition of that learned noise filter. We can see right away that the map is far denser because we're able to place more confidence in our radar returns. We're getting occupied cells on the beams on the ceiling, on the floor, on the car that we're passing that was visible in the previous map. The pillar that was missed by the previous map is now clearly represented. So this is clearly a large improvement over the original method. Lastly, this video demonstrates my full radar state estimation and mapping pipeline in use. The sensor pose is estimated by integrating velocity and orientation estimates from the radar inertial state estimator. We can also see raw radar returns. Those raw returns projected onto the image stream from an onboard camera, and some motion primitives that are evaluated by a simple local planner. We can see the radar inertial state estimates provide good local short-term relative motion estimation, and the obstacle detections clearly represent walls, door alcoves, and other salient features of the environment. Now, because both the state estimation and obstacle detection methods are purely radar-based, or radar and inertial-based, they're not going to be affected by any kind of perceptual difficulties like darkness, smoke, or fog. So a system such as this could be used to aid a small agile robot in navigating such visually degraded conditions. So in conclusion, this work demonstrated an accurate and consistent radar-based state estimation and obstacle detection method. And it shows that the use of radar for these problems on small agile robotic platforms is possible. I believe it would be very interesting to continue developing these methods and start demonstrating them in real challenging field robotics scenarios. Thanks all very much for your attention.
Daniela.
Yeah, so thank you for this.
The microphone.
I'll just speak loudly.
It's for recording.
Okay, so studying how to respond in inclement weather conditions is very important for robots. And it's very interesting to see how you can handle fog. Have you tried using this method with rain or with snow?
I haven't tried specifically with rain or snow, no. I did some experiments for this paper, which are documented in the paper, on mapping quality in varying levels of fog density, but they both didn't have the time and they weren't visually compelling enough to include in the presentation. But we haven't done experiments in rain or snow.
Two more questions, yeah. One in the back, and then Philippe. Yeah, just Philippe, go ahead. Because
I don't know if that radar slum-based dataset already exists for comparing the performances of your algorithm.
Oh, there actually is at least one data set that I know of that could be applicable for further testing this and other radar state estimation and mapping methods because it was my subsequent project to this one was released. It's called the Color Radar data set, and it includes basically the same kind of information that was used in this work, as well as higher resolution imaging radar for sort of further iteration on this sort of method. But such data sets are rare, but they are beginning to become available.
There is one called Kitty. Do you know it? No? And my question is, did you try to use those data sets to evaluate the performances of your algorithms?
So I guess two things. I wasn't aware that Kitty specifically included radar data, but
there is one radar-based data.
there are several data sets available that include radar data. Most of them are, it's difficult to apply them to this problem specifically because I think at the time this work was done, all of the available data sets that included radar were focused more on autonomous driving. So we're limited to 2D environments and used radar sensors of a type often that wouldn't really be usable on a small, lightweight aerial platform. So that's why that wasn't incorporated in this work.
One final question.
The learn filter, do you think it would work, because it seemed like you're mostly using it in like a structured indoor environment. Do you think it transfers well to like outdoor environments or unstructured environments, or would you need to retrain that? Because it seemed pretty critical for the approach.
So what I demonstrated was in a indoor parking garage environment, but the training data set that I gathered to train it gathered from strictly indoor environments to that parking garage to outdoor environments, and it generalized fairly well to at least all of the environments that it was specifically trained in. I don't believe I evaluated whether it was applicable to an environment that like an environment type that it had never seen before.
That it learned?
That is, I think, and also fervently hope that that's what it learned,
Sure.
Yes.
Okay, I think in the interest of time, we should carry on. Thanks very much again, Andrew. And can you switch to the... Okay, perfect. And I see our good friend, Simon Lacroix, is presenting a paper from ENAC Toulouse and LAS CNRS, experimental flights of adaptive patterns for clouds exploration with the UAVs. Bonjour, Simon. The floor is yours.
Bruno, thank you very much for the introduction. So I'm sorry not to be with you. I'm in gray Toulouse, rainy Toulouse now. I hope it's better in Malta. Yeah. So very quick word about all the authors. Actually, this project was mainly led by atmosphere scientist people from Météo France, the research center of the French weather forecast. And so I'm from LAS, I'm a roboticist, and the people from ENAC, colleagues from ENAC are working on drones, and they have developed the Paparazzi autopilot, which is an historical one. So a few points of context. There are many atmospheric phenomena, and this is not exhaustive. Here you see just a few examples. And most of them remain quite unknown for the scientists. They don't understand really all the physics that is happening within such phenomena. And for either scientific purpose or for operational purpose, like to predict the future evolution of such phenomena, it's very valuable to gather data. And most of the data we have on such phenomena are remote data coming either from satellites or from the ground. There are some in situ ways to gather some data, some in situ data. This is with balloons, but they are not controlled. UAVs, with respect to all these ways to gather data, have many advantages. So they gather in situ data, and they are able to be controlled, so to gather relevant data for the purpose at hand. And this has been known and observed, of course, by the atmosphere scientists for long, and they have a society, a scientific society, which gathers something like 100 people of atmosphere scientists who use drones, and they gather once a year in specific places to exchange on what they do. But these guys are not roboticists, and they use drones the way they buy them. And there is definitely a lot of interest into developing further processes to explore such phenomena. And one of the most interesting things is the ability to deploy fleets of UAVs to gather denser data, to gather more data, and of course, synchronize in time. And this is true whatever the purpose is. Is it be it for scientific purpose or for operational purpose? Probing the system with more data yields better observation and better prediction, of course. So you may think, okay, it's a classic multi-robot exploration problem. I built a map, I find the ways where my map misses information, and then I decide to go there. The thing is that these environments are so different than any usual robotics problem, is that it's definitely not a classic multi-robot exploration problem, especially from the mapping point of view. I'll say a few words about this. And so I will present the objective of a specific project, very briefly, some elements of solution, and I will insist a little bit more on some experiments we carried on 2 years ago and draw a few lessons. First of all, we are interested because our colleagues, atmosphere scientists, are really interested in understanding what's going on into cumulus clouds. And there is even actually a scientific controversy in the community as to what exactly happens in there. So the microphysics is well understood, but the global phenomenon on the so-called entrainment and detrainment, which is the cloud gathers some water inside and also water goes out of the cloud, are not well known. And everything that is interesting actually happens at the interfaces between the cloud and the atmosphere. And so discussing with them, they really specified some things they want to do. Since they would like, for instance, to map horizontal section, so as do this with 2 UAVs in a synchronous manner at 2 different altitudes, so that to estimate the bandwidth, for this is not the word, so the volume of water that is going high in the cloud. They are also very much interested in perceiving what's going on at the interfaces. And for this, they are interested in a series of variables, so pressure, temperature, humidity, liquid water content, aerosols, and of course wind. I mean, these phenomena are very windy phenomena. The wind drives the phenomenon, and the phenomenon itself, the physics itself, also generates wind. And so with them, we have defined what we call flight patterns, basically to answer this kind of high-level task, like measure cloud 8, or track the cloud border, either to get some data to measure its diameter, or map horizontal sections. And so the flight patterns we have developed are quite simple. They basically exploit a sensor that tells the system whether it's in or out of the cloud. And doing a simple kind of bang-bang control scheme, we can drive a UAV so that it goes along the border of the cloud. We can use the same, so transitioning with a sensor that is able to perceive the transitions, the cloud border, to define some horizontal mapping scheme of a section of the cloud. There is one little point which is important here, is the estimate of the cloud center of mass, which can be obtained thanks to building maps. So I will just say a few words about building maps of clouds. So basically the sensors we have no look ahead. We don't have LiDARs, we don't have cameras. All these are totally useless in clouds. We only have sensors that do perceive data where the drone is. And we are trying to map a dynamic 3D phenomenon on the data that are gathered along trajectories, say 1D manifolds. So it's a highly uninformed mapping system. But there has been some work in the literature, and we have pushed a little bit, is to resort to Gaussian process regression to extrapolate basically data on inserting some knowledge, say it's naturally model-free GPR, some knowledge on the regularity of the cloud or its size, for instance. And this here shows a few illustrations, say with just one UAV, one black dot here with one data, at time T1, we can, well, predict that the cloud is like this. And after having made some these trajectories, we can complete a map. And a very good thing with GPRs is that it does provide an estimate of the quality of the map. So, but from this, in this project, for now, we only derive some very coarse cloud parameters so as to drive the flight patterns that goes, for instance, along the trajectory, along the border of the cloud. The overall thing is integrated with a system in which the users play a large role. I will come back a little bit to this later. And so now let's move to the experiments, because well, it's Iser after all. So, well, first we could make some trials near Toulouse. Unfortunately, not in clouds. It's not that easy to have clouds at low altitudes. But thanks to the overall integration scheme, we can deploy some hybrid real UAVs flying in virtual clouds that are the results of heavy simulations from the atmosphere scientists, and then to test the deployment on the pattern process. So here you see one UAV not flying very high. This is the map. I think on the left it's a map, maybe on the right it's the cloud ground truth, the simulated one, on the ground control station. But now we moved to Barbados in early 2020, almost 2 years ago now. So why there? So not because it's a sunny place, but because it's a windy place actually. Because this is the most east island of the Western Indies, and as such it's the first to encounter the winds that come from the east, from the Ocean Atlantic. So all the phenomenon behind actually are already perturbated by the Barbados. And so this is why we decided to go there, and also actually because we joined to a huge experimental campaign from atmosphere scientists. We used manned planes, other big UAVs, satellites, boats, to gather some data, and so we took the opportunity to participate to this campaign. There's of course quite a lot of logistics, so it required all in all nearly 10 people during 4 weeks. Everything had to be shipped beforehand. On the flight, so this was our playground. Basically, we took off from a green area close to the beach. We are looking eastward here. This is the flight zone that was allocated to us, 15 kilometers long. And the strategy, well, I will say later about the strategy. Very interesting is the place of the humans in such experiments. First, we have the atmosphere scientists that are here to say, okay, I want this, I want to map this, I want that the UAV moves up at this elevation and so on. So they basically task the fleet, they give the commands. We have a guy that supervises the map making software. We have an UAV operator behind the screen who monitors the flights, battery levels and so on. We need a safety pilot to handle, well, basically takeoff and landing. And we have an overall flight director. So all in all, for just one UAV or two UAVs, a very small fleet in the air, it requires at least 5 people. The airframe so it's a commercial one, easy one, equipped with, say, classic pressure, temperature, humidity sensor, a specific sensor, which you see here in the insert, which is able actually to measure the content of liquid water content, the content of liquid water in the cloud. We could use long-distance serial modems, and we flew the Paparazzi UAV autopilot. For this kind of thing, robustness is key. You don't want to spend time on the terrain to repair your UAV. So even though we had conceived a high-end Formula One UAV able to fly 3 hours, we decided not to fly it because it was way too fragile. The flight strategy was basically to take off, move away eastward, and set the UAVs in waiting patterns so that when the cloud comes, they detect it and they track it back to the beach. So a little bit more precisely, each flight plan consists of a sequence of steps from taking off, wait, raise, and then put in the waiting pattern. And once a cloud is detected, thanks to the mapping system on the cloud, the liquid water sensor, then we trigger on the sensor-based adaptive flight pattern. And in this case, we were only able to try actually the patterns that track the cloud border. In summary, so these are the plots of all the flights. In some numbers, maybe the most interesting one is that we could gather 45 hours of data for our colleagues, for our atmosphere scientists. But actually, we spent most of the times where, preparation flights. So we had to calibrate the sensor. We had a lot of issues with this sensor, actually. And we also had some hardware issues. So I would say we flew only half of the flights, actually gave some delayed data. This is an illustration of a successful flight in which a cloud has been caught by the two UAVs. On the two UAVs, when you see this weird trajectory, it's actually the application of the border following pattern, which you see here. on the trajectory shows the data that is in cloud, out of cloud, so it's pretty hard to understand. But everything is under an east wind of 8 meters per second. So reporting everything on knowing an average value of this east wind, which is very constant, in the cloud coordinate system, this is the result of the data acquisition. So what you can see is that the cloud is not a round shape, either a square or whatever. It's always complex, very complex shape. And thanks to this, for instance, in this case, our colleagues from Météo France said they could derive some very interesting scientific results, which I won't develop here, and I would not be able to develop them very precisely, but they were extremely happy with the data they had, and they say it's the first time in the world that we do have such data, with only 2 UAVs. So now from the lesson learned, well, everyone knows in this room, in this conference, that there's a huge difference from a concept to drawing on a table on life. So a cloud, on this one is a particularly vicious one, I should say, because it has definitely not well-defined contours. But even in the big clouds you see in the sky, I mean, their contour is always like this. The sensor is very noisy, there's a lot of hysteresis effect, and so this is the raw data from the liquid water sensor that tell us whether we were getting in or going out of the cloud. So life on the terrain is really, or in the air, it's really different than in the lab. A few points. Well, of course, logistics is an issue. We lost too much time in finalizing the preparation of the UAVs. And in the end, we could only have 2 UAVs at the same time. So that's quite disappointing. We had 5 UAVs on the ground, but we have never been able to take off even 3 UAVs because of some sensor hardware failures, and also because of a little bit poorly thought overall system, because the operator and safety pilot workload really becomes huge when you have several UAVs in the air. Of course, searching blindly for clouds is inefficient. So I mentioned vision is totally useless to map a cloud, but when you're outside the cloud, to estimate its distance, its shape, its size using, well, classic, I would say, vision algorithm, it is possible. And this is definitely on our very next agenda, is to be able actually to locate clouds and not to wait for them blindly. About the tracking system also, because so the contour being not well defined, we now have defined an automatic recovery system to retrieve the cloud when it lost it. That's about it. Just a last slide to mention that actually there's a whole research program behind this, because we are very far from gathering all the data a fleet of UAV could gather in such system. Volcano plume or any kind of pollution plume or any kind of cloud, actually. So there are a lot of things to be done. The one that do interest me in particular is the mapping, and also decision, being able to do adaptive sampling, and not sample blindly things. I have some dots here. There are many things, not to mention all the logistic issues like communication plus regulatory, which is an issue. The thing is that, well, as you all know, everything should be done in tight collaboration with the users, be they scientists or operation people like the civil security forces that want to track the pollution plume, for instance. Okay, I hope I did not run out of time. I'm sorry if I did.
Thank you.
Any question?
Yes, yes. Let's give a hand to Simon. Paper is open for discussion now. Yes, please. João.
Okay, thanks very much. This was great, and I don't have a question. I just want to make a comment, which is we've been doing exactly, let's say not exactly the same, but something along these lines with unmanned underwater vehicles and tracking patches of water, or, for example, plumes or coastal or ocean fronts. So I think there's lots of things that probably we can learn from each other by, let's say, looking at these problems. The interesting thing with some of these oceanographic phenomena is that you can also spot those from the air. So we've also been using UAVs, so flying to basically find the front and then tasking AUVs to go to the front and sample along the front or map it. Okay, this was just my comment. Thank you.
João, are you João Sousa from LSTS in Porto?
Yes, I'm the one.
So nice. We know each other. Of course, you're totally right. There is a huge analogy between exploring atmosphere and waters, actually. Definitely.
Okay, thank you. Sorry with the mask, it's a kind of difficult.
I mean, in all our papers, we always refer to such work. And actually, there have been, I think, more work in AUVs underwater in this kind of system more than on UAVs, as far as I know.
Good. In the interest of time, I think, Usama, very quick one, please.
Simon, bonjour.
Bonjour, Osama.
Bonjour. Je pensais au Pic Saint-Loup, il y a des vents très forts qui rendent fou.
English.
Oh, I'm sorry. I'm sorry. Yeah, well, near Toulouse, between Montpellier and Toulouse, there is an area called the Pic Saint-Loup, and they make they make very good wine. And they say this is the wine that makes you go crazy because of the wind. So, Simon, any plan for studying the wind near Pic Saint-Loup?
You know what, Osama? I'm going there tomorrow morning to meet some firefighters. Yeah. Because in this area, there are really, I mean, there are many wildfires actually.
Well, great. Get us a case of good wine.
Very good.
Thank you.
Thank you again, Simon. And,
thank you.
Please stay connected because we'll wrap up the session in the end with some discussion.
Okay.
Okay, and then we move on to the next paper. Ayai Shankar, he should be connected and he will be brought up to stage. And your paper is titled Multi-Rotor Docking with an Airborne Platform. Please, yes, you're up on stage now. Go ahead.
Can you hear me?
Yes, perfectly.
Great. Hello and good afternoon to everybody in Malta, and hello to everybody else from everywhere else in the world. I apologize I couldn't join in person. It's a great opportunity missed. But I'm happy that at least remotely I can present this work on multi-rotor docking with an airborne platform. My name is AJ, and part of this work was done during my PhD with Sebastian Elbaum and Carrick Detweiler in the University of Nebraska-Lincoln. I'm currently a postdoc in the University of Cambridge, and this work summarizes and sort of encapsulate some of the previous work that I've done. Okay. The objective, the high-level objective of the work is pretty straightforward. And the idea is to dock a multirotor with another aerial vehicle in flight. As you can see in this video that's going to loop around here, we don't consider a stationary leader aircraft, we consider a moving aircraft as well. And the idea for doing this is to be able to generalize this to systems that involve a fixed-wing aircraft, for instance. Furthermore, in this work, we will also look at how to plan such trajectories, because as you might imagine, chasing another vehicle in the air for a long period of time might not be favorable. And finally, since this is Iser, we will show not just simulations, but also some real-world deployments. And in this case, we will emulate a leader aircraft moving at a relatively fixed speed with some noise, but in realistic and outdoor conditions, which is what most of this work will try to focus on. Now, why we want to do this, I want to give you some sort of a high-level motivation, and this might be fairly straightforward to understand too. The idea is that the ability to dock multiple aircraft in flight is pretty useful if you want to consider long-range collaborative transport for smaller multirotors in the air. And we also consider this idea of collaborative exploration. So that is something along the lines of Simone's work. If you could deploy a fleet of smaller aircraft at kilometer scales through a large aircraft, and we think about this idea of being able to capture them through a fixed wing on its way back. So you could potentially deploy smaller agents at larger scales for atmospheric sampling or observations and search and rescue missions and things like that. And finally, part of this work is building towards this idea of air-to-air interactions between heterogeneous systems. So as you might imagine, if the dynamics and the kinematics of a fixed-wing aircraft are going to be dramatically different from a multirotor, and the capabilities are also going to be different. And we want to explore this. We're building up this pipeline so that we can explore this collaborative missions between heterogeneous systems that have different dynamics. So there is some relevant prior work in this domain as well, and most of them have typically focused on how you can dock a fixed-wing aircraft with, let's say, another fixed-wing aircraft by a towed drogue system. As you can see in the picture at the bottom right here, there's some prior work on sort of guidance and navigation for fixed-wing aircrafts. And the idea here is essentially to have a long towed cable and a drogue mechanism to separate the aerodynamic interactions. And essentially, you develop closed-loop controllers to chase these drogue systems and essentially dock with it in flight. Multi-rotor docking is also relatively new, though. The picture labeled 1 here is from a paper in 2018 in which researchers demonstrated how you can have a smaller multi-rotor docking and undocking with another one in the air. Although their experiments were done in a static setting, the experiments were outdoors, so we were inspired by those as well. And in general, the idea of docking heterogeneous systems is very closely related to aerial manipulation, and that is also a very well understood field. What we are looking for, however, in this work is to be able to plan trajectories and intelligently plan them that optimize certain metrics and such. And one of the key factors in multi-rotor docking is that the trajectory planning must consider interaction effects. As you approach another aerial vehicle in flight, you will be in the downwash of the other vehicle, and if your trajectory planner can account for that, that is favorable. So our approach to solving this problem is split basically into 3 parts. The first one is, the first phase essentially, is to observe the trajectory of a leader aircraft flying, as we assume, in a straight line. And then in the second stage, we plan these trajectories towards a predicted final location at a finite time horizon. And then at the end, we execute these trajectories using highly agile closed-loop controllers and a manipulator that's mounted on top of the vehicle. I will explain each of these very briefly in the following slides. But the main focus, as I said before, is on this idea of trajectory planning and intelligent trajectory planning. And as you can see in this animation that is going to loop here, the leader aircraft, we assume, is flying in a straight line, relatively straight line with a constant velocity. And the follower aircraft observes it for a while, plans its trajectory to dock with it in the future, and executes that trajectory. Now, the reason why we want to think about planning is actually something that I mentioned before as well. The flying in close proximity introduces air-to-air interactions between 2 multirotors. There will be aerodynamic downwash effects as you get close to the docking point, which you must at some point. And finally, this points to the idea that chasing another vehicle for a long period of time is probably not favorable. And so we look at this problem from the perspective of a trajectory planning problem. And the idea for trajectory planning, as I mentioned before, is to not only plan intelligent trajectories that optimize certain metrics, but also account for uncertainty in the estimate of the leader. As I mentioned, when we do these experiments outdoors, there's going to be noise, and we can assume that the leader is flying in a relatively straight line, but there are errors in estimation. And therefore, we go back to this original animation where we have made these assumptions, as I stated before, and we plan this trajectory. One of the defining factors of our work is that the trajectory planning is relatively fast and can be done entirely on board. We can evaluate hundreds of trajectories in less than a second, and that allows us to keep multiple trajectories as a library and select them on the fly as our estimates for the leader changes in the future. The prediction part is something, as I've shown in this picture here, from the top-down view. We assume that the leader is carrying a towed docking platform, as you can also see in the picture here. From the top-down view, it may look like a straight line, but from a vertical perspective, our actual setup tends to sag in the middle wherever the weight is. And our platform currently has a GPS sensor mounted on it and also has a visual tag on it. And the follower vehicle observes both of these data points and fuses them optimally. The sensor fusion is essentially done through a standard Kalman filter, but the actual estimation and the prediction is done through a least square regression method, as you've seen here. And the lateral plane estimation is done as a straight line, and the vertical plane is estimated as a quadratic polynomial here. Then the planning method that we propose is also taken from some of our prior work, in which we propose a multi-objective cost function, except that, and we use this variational minimization principles, and we basically borrow techniques from variational calculus to construct these trajectories. In this particular work, we drop some of the terms from these equations and simplify a base case simplify them to a base case scenario where the trajectory minimization is a single functional minimization problem. And it essentially boils down to an energy optimal trajectory in this case. But as you might imagine, the cost function can be defined arbitrarily, and you might include terms that involve proximity to the leader and things like that. Planning these trajectories and evaluating them on the fly is pretty fast on a small onboard computer. As the picture shows here, if we assume that the leader starts in that top left corner on a small bubble, and we assume a straight line, basically a constant velocity, and we assume that the leader can end up in this larger space at the bottom right, we can plan all of these trajectories in the beginning, and then we can and we can choose trajectories on the fly as we refine the estimates of the leader as we progress. The actuation part for the implementing the actual docking, there are two parts to this. First is we require a high fidelity and high precision flight controller that can work outside in realistic conditions. And for this, we use Freya, which is part of our prior work as well. And this allows us to fly efficient, high speed and agile trajectories outdoors in practical conditions as well. And then for the actual docking part, we developed this really fast actuated servo system that docks with the leader platform as it makes even the tiniest contact with it, essentially. Our actual experiments are shown here in this video. We conduct 2 sets of experiments, a total of 25 experiments outdoors under varying conditions. Here you can see the docking is demonstrated in a static platform. And again, we don't really assume that the leader is static. We just let the follower estimate the velocity, which in this case should be 0. And we let the planning algorithm take full control of the quadrotor to dock with it. And as I promised earlier, the actual docking experiments with the moving platform are also done under varying operating conditions outdoors. And we emulate this leader platform moving at different conditions. And the entire computation, estimation, and planning is done on board the quadrotor. I want to quickly talk about some of the results from our experiments as well. The prediction error, the forward prediction error of the platform is shown here. And as we can see, with about 5 to 6 seconds of observations, we're able to converge on the actual location, actual predicted final location of the leader aircraft. And on the right, I'm also showing you the trajectory tracking performance of our vehicle. And as you can see, the experiments have been conducted under varying speeds of the leader aircraft. And in all the cases, our tracking performance with these high-speed trajectories even is under 5 centimeters in outdoor environments, which is very favorable for our experiments. And then in the paper, there are a few more results, a better characterization of our experiments and such. And here, there are 2 more sample figures that I wanted to show you very quickly. The docking horizon that we set in our missions is between 7 to 9 seconds, and we let the follower choose an optimal time to dock and plan these trajectories. And we repeat our experiments for different speeds, but also starting at different initial conditions. So in the figure on the right, the black trajectory is the trajectory of the leader platform, essentially moving over the same line multiple times. And the reddish curves are all the follower aircraft starting at different locations. What you don't see is a 3D view as well, in which all of these are positioned slightly at different altitudes as well. Finally, there's some future work that we have also started along these lines. In this work, we didn't consider the idea of obstacles present. If we want to scale this up to large-scale scenarios, you might imagine that there might be buildings or trees on the way. And some of the later work that we have done afterwards includes the ability to replan these optimal trajectories as new obstacles are discovered on the fly. And we're in some of our future work, we'll also look into how a dynamic collaboration between a leader and the follower aircraft can also be favorable for some of these docking missions. So in our experiments, the speed of the leader has been brought down quite a bit. Now, if you're actually considering a realistic fixed-wing aircraft, we might imagine trajectories that are favorable for both, in which case you might need this sort of collaboration between 2 vehicles. That is all for me. Hopefully I didn't go over time, and I'm happy to take some questions. Thank you.
Thank you so much, Ayai. We had a small glitch during the presentation that the connection here locally was just the screen, not your voice. So, but we were able to catch up. We have a question.
Yeah, thank you very much for a very interesting presentation. I would like to ask if you did you take any measure to eliminate this downwash effects? Did you apply a specific control methodology? So I'm also working with this, like under this aerodynamic effects, and wondering if you did any special method to eliminate them. Thank you.
Yeah, thank you so much for the question. It is a very important and very sensible question actually in this domain. And our approach actually tackles this from 2 perspectives essentially. One is the controller that we use. It has an onboard Leuenberger estimator, which estimates these external disturbances on the fly, and we can model the entire aerodynamics disturbances as a bulk disturbance, and the controller essentially tries to fight it. But the more important and the more relevant part of this work is in planning these trajectories that, as I showed you in the cost function earlier, we embed a metric that allows us to keep maximal separation from the leader for as long as possible, and then dock with the leader in the final T seconds or so. So the optimal trajectories are planned in such a way that for the longest time horizon, we stay away from the downwash region. And then for the shortest time possible, we quickly go in and dock with the leader. So these two-part trajectories are our solution to avoid the downwash problem.
Any more? Yes, please. One more question.
Thank you, AJ, for the nice presentation. I had a quick question on the leader selection. I'm not sure how you select the leader if you have multiple robots. Do you just currently perform a random selection from the set of robots to be the leader, or do you have some special logic in there to select the leader?
Okay, interesting.
Thank you.
If I understand the question, you're considering a case where there are multiple robots, multiple leaders, and multiple followers. But in this particular work, we only have one leader and one follower. The idea is that the leader is a carrier or a mothership that can potentially dock multiple aircrafts on the fly. So the selection of leader is unique. There's only one leader aircraft.
Yes. Yeah. So if you have multiple robots, and so in your method, you select one leader, and how do you determine that which robot becomes the leader? I think that's the question.
I'm sorry, I'm not really sure what the question is. The leader aircraft is a pre-assigned leader,
Okay,
let's say.
it's pre-assigned.
Yeah.
Okay, it's
right, sorry.
defined. Okay, got it.
Yeah. There's one aircraft that is going to be the leader.
Okay. Thank you.
Yeah.
Great presentation. I'm just curious about whether you are also looking at and flying together once you're docked, and how many different units could you dock at the same time?
Yeah, thank you so much. The idea of docking multiple aircraft, multiple smaller aircraft, I think that we haven't gotten to that stage yet. We've been able to undock multiple aircraft at strategic locations and such. I think the bigger challenges in docking multiple aircraft is mostly engineering and trying to. The picture that we have is the leader aircraft essentially reels them in, stores them somewhere, and then reels out the docking platform again, because we will only have one docking platform. So in order to do this collaboratively over a larger space, the idea is that the fixed-wing aircraft will spool them in once they're docked, and then spool out the docking platform again.
Any more? Okay, I think we should thank Ajay again. Thank you.
Thank you.
And we move on to the next presentation, coming from New York University, is Guanrui Li, Design and Experimental Evaluation of Distributed Cooperative Transportation of Cable-Suspended Payloads with Micro-Aerial Vehicles. The floor is yours, Guanrui.
Thank you, Professor. Can you see my screen now?
Yes, very well, and we hear you well as well.
Great. Okay, so it should be full screen now. Oh, actually, it's not.
As before, just go back to PowerPoint and put it in the display mode, in the projection mode, ahead of sharing the screen. Yeah. Okay?
Yes.
Are you sharing?
No, not yet.
Okay.
Okay, now it should be good.
Perfect. Perfect.
All right.
Go ahead.
Cool. So, hi everyone. I'm Guanrui Li. I'm a PhD student from NYU. Today, I'm going to give you a talk on our experimental research in 2020 on distributed cooperative transportation of cable suspended payloads with MMVs. So this is the outline of today's talk. First, I'll give some introduction of this work, and then I'll talk about the methodology being used in this experimental research. And now after that, I'll present the experimental results. And then if we have some extra time, I would like to also show you our recent development over this 1.5 years. And finally, I'll conclude the works and present some future work as well. So first of all, why do we need aerial transportation? For example, in congested urban ground during rushing hours, aerial vehicles actually can explore the free highway in air to provide faster package delivery. And also, actually, a recent Nature journal reports that small drone actually consumes least energy per package compared with other types of delivery vehicles. It's sort of like proving that small drone package delivery is actually an energy efficient solution for delivering packages. And then the next question will be, why are we interested in multiple MAV transportation? Well, first of all, potentially it can give us autonomous delivery of heavier and larger packages compared to single drone solution. And also potentially it can also give us extra resiliency with respect to robot failure. So why are we interested in cables? There are so many different types of connection mechanisms that exist in research literature that would use to transport payloads, like grippers, passive rigid joints like magnets or rigid joints in general, or ball joint. But actually, compared to all these kinds of connection mechanism, cable is actually the most lightweight and also requires simplest mechanical design. So it's very suitable for MAV platform. And also compared to active gripper, it doesn't require extra actuation mechanism. So it doesn't require extra energy to actuate those mechanisms. And also in general, compared to rigid connection, it provides faster attitude response as well. So now I'm going to present some technical approach of this research. So this is the system overview of the entire system. So we first have a payload planner that would on each robot to generate the desired trajectory for the payload, and they will send to the payload controller to decide the cable's tension vector in the 3D space. And then the robot controller will take this desired value and then take the local information of the cable direction and cable direction velocity, as well as the robot's own orientation to decide the thrust and moment that it wants to exert on itself, and then further affect the payload's motion. And then the state estimation are all being done in Vicon to provide real-time feedback to the controllers. So as you can see, this is a very complicated system. It has so many states that we like to control. So first of all, for the payload, we would like, since it's a rigid body payload, we would like to control its own a position, velocity, as well as the orientation and angular velocity as well. And for each individual quadrotor, it also have several states that needs to be controlled. First, it's the cable direction and the cable direction velocity, and then the orientation of the robot and the angular velocity of the robot as well. So first of all, let me talk about the payload controller. So the payload controller is essentially just take the desired position and desired velocity and acceleration of the payload as an input, and then take the payload's position and velocity as feedback to generate forces to maneuver the payload in 3D space. And then for the orientation motion, it will also take the desired orientation, angular velocity, and angular acceleration as input, and take those orientation and angular velocity feedback from Vicon to generate the moments to maneuver the payload for orientation as well. So now the question will be, once we have the desired force and moments to maneuver the payload, how do we distribute those force and moments into individual tension vectors that belongs to each robot? So essentially we use the distance vector from the attach points to the center of mass of the payloads, as we shown in this green vector here. This is essentially just the geometric information of the payload. And then we construct a B matrix. Actually, you can see here, it's involved the payload orientation and also the distance vector of all the attach points. And then we map, and then use this B matrix, we map the desired force and moments into individual tension vectors. So now each robot has own tension vectors in 3D space now. So the question, now the robot needs to decide what's the thrust moments that needs to be exerted on its own. So each robot just locally estimate each robot take the desired tension vectors, and in addition, the desired acceleration at the attach point, which can obtain from the desired trajectory of the payload and also using the geometric information. And it will just estimate its own cable direction and cable direction velocity, and also its own orientation and angular velocity. So as feedback to the controller. So it doesn't essentially talk to other drones to like decide its own thrust and moment. So then the thrust and moments are being exerted on the robot and then further maneuver the payload. So now let me talk about experiments. So first we did a step response experiment using different cable lengths. The purpose of this evaluation is that we would like to investigate the relative mobility between the robot and payload and the system response with respect to the mechanical setup in the system, in this case, our cable length. So as you can see in this video, first we did a step response in Z direction, and then step response in Y and X direction. So actually, as you can see in the video and also in plots here, for X and Y direction, shorter cable actually respond faster than the longer cable. And also like the longer cable case oscillate around the desired value larger than shorter cable. So this is sort of our insights in this kind of system that actually shorter cable can provide faster system response. Another thing that worth notice is that the cable length doesn't affect the step response in Z direction at all. So this also makes sense because in the controller, the Z direction, the cable length doesn't affect the thrust magnitude. Now we did several trajectory tracking experiments. Like here, we track a circular trajectory with controlling the payload in different pitch angle. We control, in the left case, we control the payload at 0 pitch angle and 0 degree pitch angle. And the right-hand side, we control the payload with a 15 degree pitch angle. And you can see here in this table, it's actually like tracking the trajectory in a very small tracking error. And similarly, we also did trajectory tracking results in Lisa's true trajectory. So which is basically infinity, like infinite shape trajectory in plane. We also we do 2 cases. One case, like the payload is controlled at 0 pitch angle, and the second one is like 15 degree pitch angle. Also, the tracking error is relatively small. So we have some extra time. So I think just 9 minutes now. So I also would like to introduce a little bit about our recent development that we actually accepted in Rao paper last year. So in this paper, basically, we developed a fully onboard state estimation methods that replaced the Vicon in the previous Iser work. So this entire system now is fully autonomous using onboard sensing only. So in the experiments here, we're actually able to also track the circular trajectory without any Vicon marker. And the robot is running VIO onboard, and also they use the local state estimation to estimate the cable direction. And also the payload geometry, actually. So this is experiments that in this paper, and if you're interested, you can go take a look at our Rao paper last year. And actually, another contribution of this entire work is that the complexity of both control and state estimation methods is less than O(n) squared. N is the number of the robot. So basically, this means that actually this kind of system is scalable computationally, it's scalable to a team of robots. Finally, the conclusion. So we first show the possibility to transport a rigid body payload to follow a given trajectory cooperatively by a team of micro quadrators in distributed fashion. So basically, each quadrator decides on force and moments using local information only. And the proposed control approach is actually quite robust to different cable lengths and able to let the payload follow desired trajectory with very small control errors. And finally, some of our insights into this kind of system is that the cable length affects the maneuverability of the system. By decreasing the length of the cables, actually you can see faster system response. But this kind of obtained at a price that you have to reduce the relative payload vehicle's mobility. This also means that the shorter cable, it seems to be more rigid. So this kind of property maybe can be exploited later on to improve sensing and also increase flexibility in different transportation manipulation tasks. So some future works could be improving the controller with considering disturbances and also use the extra degrees of freedom in control inputs to control relative configuration links. And we also interested in explore different types of connection to diversify the robot object mobility properties to analyze the benefits or drawbacks in terms of perception and control. And another interesting direction would be estimate the payload's geometric inertial parameters using onboard data only. So this is the end of my presentation. If you have any questions, feel free to ask me.
Thank you very much, Guanrui. Paper is open for discussion. Andrew.
Hello, thank you. Very interesting presentation. I'm wondering, did you only test that one type of triangular payload? And how do you think your current formulation would adapt to a payload whose perhaps its center of mass is far away from its geometric centroid or some irregularity like that?
That's a very good question. Actually, the formulation itself is formulated with respect to center of mass of the payload. So I think the irregularity of the payload shape won't affect the controller performance, as long as we just measure the distance vector from the center of mass of the payload to the attach points. But to be honest, I only tested with this kind of triangular payloads. Later on, I would like to also expand this experiment to maybe 4, 5, or 6 drones also to test different types of payloads as well. So yeah, this is still ongoing work. Actually, it's my PhD thesis. So I would like to explore different kinds of payloads as well. So yeah, does that answer your question?
There are a couple more questions. One in the third row.
Hi. Here, thanks for the nice presentation. I was just wondering how well this cable system works outdoors where you have wind. So I could imagine that you can get more swinging instabilities. Do you have?
Yes.
Have you ever tested this, or do you have any intuition?
First of all, to your question, no, I didn't test it in outdoor, but hopefully I can test it in the next 2 years. But since in New York I can't fly outdoor because the FAA restriction. So one of our collaborators actually they were able to fly outdoors. So hopefully I can test it also in outdoor environments later on in next year. But to answer your question, actually, I want to show you another work in Pennsylvania State University. They actually test this kind of system in outdoor environments. So the results shown in their paper actually also quite good. So I would say, yeah, potentially it's possible to test. Also, actually, another work in UC Berkeley also showed that they can fly in outdoor in Norwegian, in Norway. So I would say, yeah, the wind can be a challenge, but I think this kind of system can adapt to those kind of environments. But further experiments are needed, definitely. So, yeah.
Thanks.
Mm-hmm.
Thank you. Thanks for your presentation.
Thank you.
My question is to know if it would be possible to take into account possible physical or aerodynamic interactions when you will increase the rotational range of movement of your part you want to manipulate.
That is possible. For example, you can design a admittance controller on the payload. Actually, some work has been done in ETH that they actually use a admittance controller to on the payload that actually can adapt to like some extra interactions, and also, but they're using the ball joint, so it's a rigid joint, or not rigid joint, like, but essentially it's not cable. But later on, actually, another possibility of future direction of research is to think about human and robot system interaction. So how the humans collaboratively maneuver the payload with the robot also. So maybe admittance controller can be applied in this kind of system as well. So yeah, that could be one very interesting possible future direction. Yes.
Yeah, Wanrui, we have a paper with Marco Tognon and Rashid Alami from LAS.
Oh, yeah.
This is exactly what you mentioned. It's using admittance control for human-robot interaction with, you know, with basically with the drone. So it's like,
yes.
So I'm sure that you know, this work could be combined. Just two more.
I actually read Marco's work.
Yeah. Two more quick questions.
Okay, thank you.
Yes.
So you have all these tendons, and I wonder. I mean, there is an implicit constraint there that the tension has to be always positive. And,
oh yes,
do you enforce it in any way?
Yes. So this has a assumption here that the cable is always taut for the state estimation algorithm, and actually we kind of like explore the math formulation. If there's no external disturbances on the payload, this kind of system actually is always taut, because the nature of this kind of system actually. But if you have extra disturbances on the payload, potentially yes, it could be slack. Then that would be a challenging to the control methods. And also that's why maybe admittance controller can kind of adapt to this kind of place. Situation as well. So yeah, so this is an implicit assumption in this work.
Yeah.
Yes.
A very quick and last one.
Yeah, the last question is, I would like to ask, how do you solve this? Because you said that the computational complexity is like n square. Are you solving like each on board, or is there a kind of central unit that actually solves and distributes the solution to each device?
So the complexity is basically just the computation of the controller itself. So right now we actually each robot can just like obtain the desired. So right now when we were doing these experiments, actually we distribute we run the payload controller on one agent, and then we distribute the cable tension to all the agents. So basically, yes. So, but in general, I don't know like if this answers your question, but the complexity is with respect to the computation itself. So not the other kind of situation. So yeah. I don't know if this answers your question.
Yeah, okay. Then you mean actually you solve the problem in one drone and then you actually send the command. Okay.
Yes.
Thank you.
Thanks a lot again, Wanrui. We will catch up later in the discussion.
Yes, thank you.
Last but not least, we have the sixth paper of the session by Mika Kora Are you online? Yes, very good. Yeah, I thought that Baxter was Rodney Brooks' robot with Rethink Robotics, but apparently Baxter also stands for Bimodal Aerial Terrestrial Hybrid Vehicle for Long Endurance Versatile Mobility. Please.
Yeah, I guess now it does. Can you hear me?
Yeah. Perfect.
Okay, so hello, Iser. I'm Micah Cora. I'm a postdoc at the NASA Jet Propulsion Laboratory. Today, I'll be presenting on the Baxter robot, a hybrid vehicle capable of operation in the air and on the ground. And Baxter stands for Bimodal Aerial Terrestrial Hybrid Vehicle for Long Endurance Versatile Mobility. I'll just restate that now. This work was performed by a number of people in collaboration between JPL and KAIST. And I would especially like to acknowledge the lead author, Chris, as well as In-Hwan, who together were primarily responsible for developing and testing this platform. So we've been developing hybrid vehicles like Baxter with the goal of inspecting and exploring large environments, larger than would be possible by taking advantage of aerial operation alone. For example, this may include inspection of large structures, such as nuclear reactors, operation in mines, and generally inspection of large and dangerous environments. By taking advantage of wheeled operation, we'll be able to significantly improve endurance while retaining the ability to fly over harsh terrain and rubble, through vertical shafts and over walls. Further, we would like to be able to do so while carrying sensing and autonomy payloads, such as cameras and GPUs. Hybrid vehicles like Baxter have the advantage of drawing on the combined strengths of aerial and ground robots. As I've already mentioned, we obtained significant improvements in endurance from wheeled operation, alongside the exceptional mobility of aerial robots, and thereby the ability to easily navigate many kinds of challenging obstacles. We can also gain other advantages from the unique design of the aerial platform. For example, the spherical wheels on Baxter are also extremely effective prop guards and significantly improve robustness to collisions. Naturally, there's been a wide variety of work on hybrid aerial vehicles, such as the long endurance aerial terrestrial vehicle shown here. Here I've shown two robots from JPL, Rolocopter and Drivacopter, and F-Star from authors at Ben Gurion University, as well as our Baxter robot. One way to classify these hybrid aerial vehicles is by the type of drive system. Systems based on a passive drive, like the Rolocopter, rely on thrust from the rotors to move about on the ground. However, the rest of the systems shown here have active drive systems and move about more like typical wheeled vehicles. Generally speaking, passive drive systems are often more simple than active systems, while active systems may have more efficient terrestrial mobility. Additionally, passive systems based on a shell design like the Rolocopter may have a much larger footprint than other comparable platforms. We can also classify hybrid platforms in terms of morphing geometry, that is, whether and how the platform geometry changes during operation. We consider both the Rolocopter and Drivacopter as non-morphing, as the geometry does not change substantially aside from the rotating components. F-Star is active morphing due to the use of actuated arms to transition between aerial and terrestrial modes. Last, we consider Baxter to be passive morphing due to the suspension system on the wheel and thruster modules. In this case, the non-morphing systems are predominantly mechanically simple, while active and passive morphing systems each have their unique complexities to achieve their function. Baxter itself is also the product of an iterative design process. The iterations improve on payload capacity, sensing and compute payloads, and resistance to impacts. On the left, Tumbler is a small hybrid platform with a passive terrestrial mode, like the Rolocopter. X-Wing is a larger wheeled platform with active mobility and bears some similarity to Drivacopter from the previous slide. And Baxter, of course, is larger still and features more advanced suspension and drive systems. Now I'd like to briefly show off some videos of these two older generations. So first, I would like to look at the Tumbler platform, and here we can see both the passive terrestrial operation, so powered by the thrusters, as well as the system in flight, as we can see here. And I'll let this go on for just a few more moments. So again, this is a very small drone inside a larger cage. So here we have the X-Wing in an obstacle course. And so we'll be able to see how this platform can navigate a wide variety of mobility challenges. Hexwing is manually controlled, so the precision in flight is somewhat limited due to use of a human operator. When I show videos of Baxter later, that will be under a autonomous flight, unlike the system. But still, we're able to navigate the obstacle course. So as I hinted at earlier, the successive generations of these hybrid robots generally seek to improve resilience and payload capacities toward increasing the scope of the sensing and computation payloads each is able to carry, as well as the general autonomy of each platform. So Tumbler sits on the left, a small robot that carries little more than a flight control board. Then increasing scale and adding wheels, we get Hexwing, which now carries a Jetson TX2. And then the Baxter system I am presenting today is 2 kilograms larger, almost twice as heavy, and so introduces a suspension system to improve resilience to impacts. And this system has a much more complete autonomy payload with both a Jetson and a RealSense T265 for visual inertial odometry. And so Baxter presents a hardware-oriented approach to improving endurance, versatility, and autonomy. In the following slides, I will focus on key features such as the suspension system, which works alongside the belt drive. And these together enable development of behaviors such as landing with non-zero velocity. So again, I'll be presenting on the suspension system, the belt drive, and the landing process, each in turn. Regarding the suspension system, the increase in scale and need for reliable shock resistance for both drop, impact, and terrestrial operation motivated the incorporation of a suspension system into the aerial platform. The M suspension, so called because of the M-shaped profile you can see on the left, is a novel approach for vertical shock reduction in a hybrid aerial vehicle. Overall, this passive suspension design focuses on ease of manufacturing by 3D printing and seeks to minimize additive. Is formed by the primary arm. And further ensure that the rotors remain vertical as the suspension translates up and down. Additionally, the thick primary arm in the middle couples the two sides and serves to prevent the wheel from twisting back and forth. I don't know what happened to this video. So there was supposed to be a video here showing off the suspension system, but right now it's not loading. I'm going to reload the presentation quickly. It was showing the earlier videos, but it's not showing videos anymore. Can you see this video now?
Yeah, sure.
Awesome. Okay. I don't know what happened there. Always something. So in this video, we see a demonstration of the earlier prototype of a suspension system, and actually also an earlier version of that parallelogram, which had some issues with the twist that were solved by the M suspension. Moving on, I'd like to briefly highlight the 3-belt drive system. In the terrestrial mode, Baxter is driven by 2 DC motors, one on either side. So the belt drive serves to transmit power across the moving suspension. So on the right, I have emphasized that the intermediate axis of the drive system is coaxial with the axis of rotation of the arm. And so the belt and suspension system will rotate together. The clutch, which I have pointed out in the middle, is designed so that only one wheel in each pair receives power at a time. So it delivers power in only one direction, depending on the direction of motion of the vehicle. The clutch also serves to prevent transmission of impact forces through the belt drive. So when the suspension translates on impact, the clutch will rotate back freely, which will avoid overstretching and damaging the belt. So here we can see a short video of the drive system in action. Now I'd like to briefly introduce the components of Baxter's control system before I discuss the landing process. On the right, we can see the visual odometry system, which is important to enabling autonomous flight on the system, unlike the prior generation. And this will be important for autonomous landing experiments I will show later. I've also already mentioned the compute system consisting of a Pixhawk flight controller and Jetson companion computer. And these computers respectively control the motors for the aerial and terrestrial mobility modes. So now I will describe the non-zero velocity landing process. At the beginning, the robot will assume a predetermined height and entrance velocity. The system will then enter free fall and reorient itself to an angle theta. And the robot will fall until initial impact with the rear wheel and begin to roll. And finally, the front wheel will hit the ground. So I've illustrated these 4 stages here: free fall, initial impact, and then the second and final impact. When designing the landing sequence, we designed the angle of attack theta to minimize the maximum impulse to the suspension system. So on the bottom, we can see that the landing behavior is designed to produce equal impulses to the front and rear wheels. Now I would like to discuss our experimental results. The experiments evaluate flight performance and endurance, the suspension via a drop test, and demonstrate the non-zero velocity landing behavior. To evaluate flight performance, we perform basic maneuvers such as hovering, rectangle motions via waypoints, and manual flight. And I have summarized results for speed and endurance on the left. On the right, I have provided a comparison of endurance and speed for the aerial and terrestrial modes. In the aerial mode, Baxter can safely achieve speeds of up to 2 meters per second, but with a flight time of only 4 minutes. Baxter moves more slowly in its terrestrial mode, but for up to 30 minutes, vastly improving endurance. Now I would like to show a video of Baxter in flight. We observed some oscillation that you'll be able to see here at about 1 hertz, and we believe this was due to the suspension system. In general, we also had to adopt fairly tight control limits due to some translation of the suspension system while in flight. Now, one of the benefits of the suspension system on Baxter is resilience to impact. To test this resilience, we dropped the system from increasing heights at its full mass of 4.2 kilograms. Baxter was able to sustain drops of up to 1.3 meters without damage to components, and being able to fly after drops of up to 1.4 meters. Notably, any damage was concentrated on 3D printed parts that could be easily replaced. Also, since the landing experiments will involve free fall, this is an important prerequisite. So last, we demonstrated the non-zero velocity landing behavior. This behavior relies on both the suspension system to sustain impacts on landing and the autonomy system, including visual odometry for control. Baxter was able to perform this landing behavior, which consisted of a short free fall leading to impact while moving forward simultaneously. And Baxter was able to perform this behavior successfully and repeatedly without damage to its structure and components. To conclude, Baxter is a hybrid aerial vehicle that carries a non-trivial sensing and autonomy payload while retaining resilience to impacts, particularly during landing. And this is enabled by the novel suspension and belt drive. To take advantage of Baxter's mobility and autonomy, we demonstrated an autonomous non-zero velocity landing behavior, which depends on both odometry for autonomy and the resilient airframe and suspension system during landing. In the future, we are interested in developing an active locking suspension in order to improve flight performance by preventing the suspension system from translating during flight. Additionally, the Baxter system still has relatively limited autonomy in methods for path and transition planning, terrain traversability classification, and contact-aware planning and state estimation are all important to future work on hybrid vehicles like Baxter. So that concludes my presentation. If there's any time, I'll take questions.
Thank you very much.
Thank you.
Yeah, we have 2 questions. In the meantime, I'd like to ask Andrew to come up. He's the only presenter, physical presenter, to come up on stage. Yeah,
Hello.
go ahead with the questions, please.
Okay. Thank you, Mike. This was an excellent presentation. So one question I had was, in your presentation, you talked about non-zero velocity landing, but I'm also curious about non-zero velocity takeoff. Is it possible to do non-zero velocity takeoff with your current system?
I don't think any experiments like that were performed, at least not that I'm aware of. I don't see why that would be a problem like mechanically. Although I could imagine that could be difficult due to the low altitude with the visual odometry.
Okay, thank you.
And there's a second one in the middle.
Cool. Okay. Thank you for the presentation. So, Will, while you were talking and you mentioned your oscillation during flight, I immediately also thought of an active locking on the suspension. So it's cool to see that was in the future work. But another thing I was thinking of in that sort of realm was certain mountain bike derailleurs, for example, have a clutch to lessen motion or the speed of motion. Have you thought about adding maybe a damper onto suspension to reduce its ability to move a little bit? That might help with your oscillation while still being able to absorb the harsh impact of landing. Did that make any sense?
Yeah, I think so. So adding damping to the suspension system, is that right?
Yeah, or maybe small impulse damping. Yeah.
Yeah. I don't know that had been considered, but it does sound like an interesting idea.
Okay. Thank you.
I don't think I have much to add at this point.
Sure. Okay. It was very specific. Thank you.
Okay. So let's flow in the discussion now. I can see, can you, Mike, can you stop sharing so that we can see? Okay, great. Yeah, I see all the speakers from this session. So one issue which was discussed during the session is the autonomy. Just as like, so I'd like you to comment on where we are here with Ariel robots in terms of the autonomy, and what do you think are the big challenges to overcome I mean, when I say autonomy, I don't refer only to the autonomy of the battery, because that's a bottleneck, just affecting all kinds of such system. But in terms of the decisional autonomy, so in terms of the control. So Andrew, would you like to start?
Sure. I think my research in this area has been actually pretty limited to a small but I think important limitation on autonomy, which is the robot's ability to do its perception and state estimation tasks on board and in perceptually difficult environments, finding ways that are both finding methods that are both adaptable to different environments and are lightweight enough to be contained or lightweight enough both physically to be a payload for an MAV and lightweight in processing terms enough to be processed on the MAV have been the principal challenges in my work. But I did specifically select those challenges for my work, so take that for what it's worth.
Anyone from those connected online?
Yeah, I think I agree with Andrew as well. The perception challenges are probably the major ones. We are, as a community, I think we are making great strides in visual autonomy and such. However, doing these experiments outdoors, even for a single vehicle, is pretty challenging right now. But as we talk about teams of vehicles, doing perception on board and sort of coordinating, we're quite far away, actually.
I think another possible challenge challenges for like MAVs in general is the so all this SLAM and control algorithm works quite well in low speed flight profile. So when it turns into like higher speed, like in a RAM of like 5-6 meters per second, or even higher, it starts to become challenging for the perception specifically. But there are some works in 2018, I think the FLRA project in America, like they kind of demonstrate that you can fly MAVs like autonomously using fully onboard perception around, I remember like 5-6 meters per second, but like up like some speed upper than that, it's more challenging, I think. But maybe improving the sensors, like to kind of like going anti this motion blur, for example, would be some interesting way to solve these problems. So, yeah.
Yeah, I think I could add just slightly to that. It's not work that I've done myself, but work that I've seen on perception for high-speed MAVs using event cameras might be of particular interest there.
Yeah.
Mike, Jolene, Simon? Anything to add?
I guess if I'm following regarding perception systems, I think what's interesting for Baxter is particularly like terrain classification. So you need to be able to recognize whether a given terrain is traversable in the terrestrial mode, identify landing sites, and so on. This was developed in part for the Sub-T challenge. So we'd also developed similar systems for our ground vehicles, but not for hybrid air vehicles like this one.
Any further comment?
I think there's also challenging is that the endurance for aerial robotics. For most MAVs, UAVs, I think they cannot fly for more than 30 minutes or so. I think it's a challenging problem to solve, and many researchers about it focus on just like Michael Corwin's work, the hybrid robotics, and make it improve its endurance ability.
Yeah, this was the power autonomy. Simon, concerning like the clouds, as I recall, your vehicles were waiting for the clouds, like in a sort of idle. So, is there anything that could be done, in terms of making more intelligent and maybe link up with the with the forecast by the meteorologist?
Oh, yes, sure, definitely. Some radars can track clouds, for instance, and then warn the fleet that the big one is coming, and the fleet should head to it, for instance. But coming back to your general question of autonomy, it's a tough one because, well, as you all know, there's already a market of autonomous mapping drones, for instance, and there are dozens of companies that sell these worldwide. Everything comes, actually, the drone community has now reached a maturity that we have so many kinds of drones, from the wing that just do mapping to the one with arms that do aerial interaction, for instance. And so the term autonomy is not coined the same way for all these kind of drones. When it comes to flying indoor and manipulating the environment to make probes or even to pick up things, we still have some work to do, I think.
Well, a very interesting session, sparked a lot of interest and maybe too many questions because we are running late. Actually, we started late. So this is a heads up to the presenters online of the next session that we are running like 40 minutes late. So be patient. We have a quick coffee break, as quick as we can, and we will resume in about 10 minutes. Okay? Thank you.